Hello students, welcome to the digital learning of session 6 of unit groups of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 6, let us discuss about examples of cyclic group.
So examples on the cyclic group. So find all the subgroup of a cyclic group is fourth root of unity. Let us take the group 1 and minus 1, I and minus I is a fourth root of unity. Then G comma multiplication. G is a group under the multiplication where I belongs to G. So we have already seen. So I to the power 1 means, so that is we are verifying here for two elements, that is I and for minus I. Firstly let us take for I to the power 1, I is taking only once. So that is becomes a I. I is taking twice means minus 1. I cube becomes a minus I to the power 4 becomes the 1. So we are having all the elements which is present in the G here. 1, minus 1, I and minus I. So every element of G is of the form. So if you are observing, every element is in the form of the power only. That is I to the power n form only here. So n is equal, that is I to the power 1, I square, I cube, I to the power 4. So if we are taking like that, we are getting all the elements which is present in the G. Therefore we can say that it is in the form of the G only. It is in the form of the I to the power n. So every element of the G is of the form I power n, where n is equal to 1, 2, 3, 4. So let us verify for one more element here, minus I. As we have verified for a I, let us verify for a minus I. Similarly, as we have verified in the earlier, minus I to the power 1 means only once we are taking the minus I, it becomes the minus I. Minus I the square, twice we are taking minus I, minus 1. Minus I to the power 3 becomes a I here. Again minus I to the power 4 becomes a 1 here. That means again all the elements which is present in the G we have got it. And also minus I to the power 1 if we are taking, we are getting as a minus I. Minus I to the power 2 if we are taking, we are getting minus 1. Minus I to the power 3 we are getting, or we are getting as a I. Minus I to the power 4 if we are taking, we are getting it as a 1. That means again it is in the form of the power only. Every element of G is of the form minus I to the power n. So again here, as we have seen in I, it is also taken as a power minus I to the power n, where n is equal to 1, 2, 3, 4. So G is equal to minus I to the square, minus I the whole cube, minus I to the power 4. So that means it is nothing but we are having in the power form only. It's in the power form only. So all the values of 1, 2, 3, 4 we got it. So therefore that is here we are verifying for two elements. So those two elements are I and minus I. So if we are verifying for two more elements, so it is not that we are getting all the elements, but if we are verifying for two elements, that is I and minus I, yes, we are getting in the form of power n. So the set of fourth root of unity with respect to the multiplication is a cyclic group. So second example is, if a is a non-zero integer, then show that g is equal to a power n such that n belongs to z is an infinite abelian group with respect to the multiplication. So here a power n, the group of the or set of the a power n we are taking, where n is a integer. So integer we are taking a power z, a power 0, 1, a to the power 1, a square, a cube and so on. And since it is an integer, we can also take a power minus 1, a power minus 2, a power minus 3 and so on. So let us go for a star b is equal to ab. For all ab belongs to g here. So let a power p, a power q, a power r belongs to g. So that is we have to verify for the laws here. So let us take, to prove it for associative law, we are requiring three elements. So the elements we are taking from the group is a power p, a power q, a power r. So where p, q, r is from the integer. First let us verify for a closure law. So what is that closure law says? A star b, that is a star b, belongs to G. So taking the two elements here, that is a power p and a power q, which belongs to G, which implies a to the power p into a to the power q, that is under the multiplication we are doing, which is equal to, so that is a power p into a power q. In between of a power p and a power q, we are having the multiplication. So a power p plus q we got it. So p plus q is taken as a k here. Therefore, it is in the form of the a power k, which belongs to G. So we can say that it is in which form? So it is in the form of the a power n. Nextly, to go for a associative law. So to prove it for associative law, we require three elements. So a power p, a power q, a power r. So bracket is for the LHS side is for a power p and a power q. In the RHS side, bracket is for a power q and a power r. So nextly, since the bases are same, we can add up the powers p plus q here also in the RHS side. So a power q plus r. So on the whole, we got it as the answer a power p plus q plus r, which is equal to a power p plus q plus r only. For all a power p, a power q and a power r, all the elements belongs to G only. Therefore, G is satisfying the associative law. That is RHS is equal to LHS here. So therefore, G is satisfying the associative law. Third law is verifying identity law. So identity law here is a 1. So E equal to 1, where A belongs to G here. So if you are observing the set, in the set we have the element as 1. So if identity law we are taking as a 1, therefore yes, this 1 is from the set G only. Therefore identity law holds good. Again, take the inverse law. Let's take the element a power p here. So for the a power p, the inverse element is a power minus p. So if we are taking a power p minus p here, we got it as a power 0. So which is equal to 1. So that means there is a relation with the inverse law and the identity law. Whatever the element we got it in a inverse law, so that should match with the identity law. So in identity law we got it as a 1. Identity element we got it as a 1. So in the inverse law also we got it as a 1 only, which is equal to E. So therefore inverse law also holds good. So nextly, to verify last law is commutative law. So commutative law means taking the two elements a power p and a power q, which belongs to G, equal to a power p, a power q, which is equal to, so a power q and a power p. That means, so a star b is equal to b star a here. So therefore a power p plus q is equal to a power q plus p. But p plus q is equal to q plus p here, is it not? So for all p and q belongs to G here. Because the bases are same here, we can equate the power. So therefore p plus q is equal to q plus p. So we can say that a power p plus q is equal to a power q plus p. Therefore G comma star is an abelian group and G is an infinite set. So therefore G comma star is an infinite abelian group with respect to the n. That means it is satisfied for all the laws. It's satisfying the closure law, commutative law, associative law, identity law, inverse law. Therefore we can say that it is a infinite abelian group with respect to the n. The next example is, show that a group G is equal to 1 comma minus 1 is a cyclic group under the multiplication. So as we have already seen how to get the order here, minus 1 one time means minus 1, minus 1 twice it is 1. Then G is equal to minus 1 to the power 1, again minus 1 the whole square. So if we are taking in the power form of the minus 1, that is we are verifying for only one element here as a minus 1, so which is belonging to G. We can verify for 1 also here, But here we are verifying for a minus 1. So if we are verifying for a minus 1, we have got the element which is again present in a G only, which is of the form a power n, that is minus 1 to the power n. So minus 1 is acting as a generator of the G. Therefore, we can say that G comma, that is the set of the G under the multiplication, is a cyclic group. Cyclic group means what? So one element, at least one element should act as a generator. Here minus 1 is acting as a generator. So if you are taking as a 1, that is verifying like this, as we have verified for a minus 1. If we are verifying for 1, it may not be the generator, but at least one element is acting as a generator, means yes, of course we can say that it is a cyclic group. Here minus 1 is acting as a generator, so therefore we can say that it is a cyclic group. Next example is, show that a group Z phi under the addition modulo phi is a cyclic group and every non-zero element of Z phi is a generator. So set is, so under the addition modulo phi we have to consider of the integer. So therefore 0, 1, 2, 3, 4. Under 5 and addition modulo phi only we have to consider the elements. Therefore the set becomes the 0, 1, 2, 3, 4. So Z phi under the addition modulo phi is a group here. Since 1 of 4, that is, it is a addition here. So addition we are considering, that is 1 is taking the 4 times, right? So 4 times means which is equal to 4. So under the addition modulo 5 we are taking, the last element becomes the 4 for me. Therefore I am taking 1 of 4. So 2 of 4 means 4 twice we are taking. 4 twice. So here in the last example, 4 once we are taking, the answer becomes the 4. Nextly 4 we have to take twice. So in the bracket I have shown 4 plus 4 becomes what? 8. So under the addition modulo 5 we are taking, therefore whatever we are adding by 4 and 4, so we have to subtract it by the 5, therefore 8 minus 5 becomes the 3. So similarly 3 of 4 means we have to add up the 4 3 times under the addition modulo 5. So first operating the 4 twice, that is 4 plus 4 becomes the 8 minus 5, which is equal to becomes a 3 here. Again add up by a 4, we are getting as a 7. So this has to come below the 5 only, because it is a addition modulo 5, therefore becomes the 2. So similarly for 4 of 4, 4 times we have to take under the addition modulo 5. So the answer becomes a 1, as I have shown it in a bracket. Then 5 of 4, 5 times. So answer becomes a 0. So therefore, so if you are observing, so how many times we are taking? So n of 4 Z phi is equal to n of 4. So 1 of 4, 2 of 4, 3 of 4, 4 of 4, 5 of 4 we have taken. So we got all the elements, that is 4, 3, 2, 1, 0. That is, these all elements are present in a set Z phi. So therefore, what happens to the power here? What happens to n here? It becomes a 1, 2, 3, 4, 5. So power 1 to the power 1. So or we can say 4 to the power 1. So 4 to the power 2, 4 to the power 3, 4 to the power 4, 4 to the power 5. So like this, if we are taking in the form, that is in the form of the power, so my n is equal to 1, 2, 3, 4, 5 we got it. So 4 belongs to Z phi. So therefore it shows that every non-zero element of Z phi is a generator. So that means generator means what? It should generate all the elements what we have taken in a set. So the set we have taken as Z phi equal to 0, 1, 2, 3, 4. So the element I am considering to show it for a generator is 4 here. Yes, 4 is acting as a generator. So therefore Z5 is a generator. Let's take the definition of the Euler's function. The number of generator of a cyclic group of order n is called the Euler's function, and it is denoted by pi of n, and it is defined as pi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 upon p2 and so on, where p1 and p2 are the prime numbers. So here why we are taking the Euler's function means, so this in the cyclic group, to explain about the cyclic group, we were taking the generator, the word generator. So related to the number of generators, so we have to define in the form of the Euler's function here. Therefore Euler function with the prime numbers, Euler function in the form of the prime numbers. So I'll again explain the Euler function here. It is nothing but number of generator of the cyclic group of order n, which is called as a Euler's function, and it is denoted by pi of n here. So in the cyclic group we were telling that if at least one generator exists, then that group will be called as a cyclic group. So here number of generators of the cyclic group of the order n will be the Euler's function. So therefore it is denoted by pi of n, and it is defined as the following. So example for the cyclic group. Find the number of generators of the cyclic group of the order 60. Let us take for a first element, first number, that is n equal to 60. So 60 can be taken as, we can split it as the 2 square into 3 to the power 1 into 5 to the power 1. Remember that it has to be the prime elements only. We have to consider for our prime elements only. So P1, P2, P3. So P1 is 2, P2 is 3, P3 is 5. The bases are, we have to be taken in the form of prime numbers only. So to explain it for a number of generators or to apply for a Euler's function, we have to consider only the prime numbers. So therefore 60 is taken as 2 square, 3 to the power 1 and 5 to the power 1. So applying the Euler's function formula here, pi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 and so on. So what are the P1 values? P1 values are 2, 3, 5. In place of P1, we can substitute 2, 3, 5. In place of n, we can substitute as a 60. So after operation, so we got it as a 60. So this is the number of generators of the cyclic group 60. Okay. So of the orders, so they have asked us to show for us the 60 here. Therefore number of generators of the cyclic group of the order 60 is 60. Number of generators are 16 here. For the next number 8, the order here is 8, 8. Let us check how many generators we are going to get for a 8. So n equal to 8 here, G be a cyclic group of the order 8 with the generator A. So as we have already seen, we have to express in the form of the prime elements only. So 8 is equal to 2 cube. We can express in this form. Therefore, again, what is the Euler function formula? N into 1 minus 1 by P1. So no need of taking 1 minus 1 by P2. Second element is not necessary to take. So therefore, 2 cube into 1 minus 1 by 2. Right? So what is my P1? P1 is 2. So we don't have a element of P2 here. Therefore, no need of taking the second term, that is 1 minus 1 by P2. So after simplification, we got it as a 4. So number of generators are 4 for the order 8. So what are those? It is a cube, a to the power 5 and a7. So these are the number of generators. So next the example is, find all the subgroup of Z18 under the addition modulo 18. So Z18 under the addition modulo 18 is a cyclic group of the order 18 with D as a generator, and under the addition modulo 18 only we have to consider as a elements of the set, that is from 0 to 15, sorry 0 to 17. So order of Z18 is equal to, including 0 we are considering, therefore number of elements will be 18 here. The order of Z18 will be 18. So firstly we have to go for a divisor of the 18. Divisor of 18 are 1, 2, 3, 6, 9 and 18. So subgroup of Z18 are any subgroup. So take it for 0 and 6, 0 and 9, 0 and 18. 0 and 6 under the addition modulo 18 here. That means, so we have to add up 0. That means what we are doing, we are taking the elements of the set Z18. The first element is 0 here. So we are verifying for 0 only here. So 0 plus 6 becomes what? 6. But this comes below the 18. Therefore, we are writing as a 6 only. Nextly, 0 and 9 is there here. So add up 0 and 9. This has to be, the answer has to be below the 18. So yes, it is below the 18 only. Therefore, 9 only directly we are writing. Then 0 and 0 plus 18. The answer has to be below the 18 here. So it is not below the 18. Therefore, 18 minus 18, it becomes a 0. So similarly, the H1. So that is 1. So the elements becomes, so here, how many elements we are going to get for this? So it is a 0, 1, 2, 3 up to the 17 we are going to get. So second element, so 0, 2, 4, 6, 8, 10, that is, it is the element, it is divisor of the 1. So 1, 2, 3 up to the 17 we have got it. Nextly 2. So 0, 2, 2 2s are 4, then 2 3s are 6, 2 4s are 8, like that we got up to the 16. But element has to be below the 18. Here the element below the 18 only we got it for the divisor of the 1, right? So then nextly for 3. So below the 18 up to 15 we got it. So here below the 18 means up to the 12 we got it. Below the 18 up to the 9 we got it for a 9. H5 for H6. So below the 18 means it becomes a 0. So these are the subgroup of Z5 under the addition modulo 18.